Welcome to the lecture on delta modulation, the topic which was pending. I will start with the motivation behind it. So you all know that what we have been doing till now. So suppose we have some signal, okay, so we sample it, and then after that those samples are quantized into different levels. Then let's say that this point corresponds to some number, suppose 4. So it is a voltage level of 4, and let's say this point has a voltage level of 8. So how many bits will you need to represent to transmit it? Suppose if we map this 4 to, of course, 1 1, okay, and this 8 will be mapped to 1 1 1. So how many bits do we need? We need 2 bits to transmit 4 and 3 bits to transmit 8. Now let's see if we do, instead of doing this, if we first of all increase the quantization level, we can maybe improve it. Okay, so let's say that then the next level we have here after quantization, let's say that is 6. Fine. So how will we map 6? So 6 will be encoded to 1 0 1. Fine. Now instead of doing this, if we do one thing, suppose, okay, in the first instance we transmit 4, so we need 1 1 2 bits. Now instead of transmitting the next level 6, what if we transmit 6 minus 4? 6 minus 4 is 2, and 2 will just need how many bits? You can represent 2 by 1 0 2 bits. So what strategy we will apply at the receiver is, the receiver has first received 4, then receiver has received the difference of the 2, so it will do 2 plus 4, so receiver will get 6. You see, we have conveyed the same information, but we have used less number of bits. With just 2 bits, we are able to convey the next quantization level. This is the whole idea behind a technique which is the enhancement of pulse coded modulation called differential PCM. And it is differential PCM, which is a generalized concept. A special case of differential PCM is called delta modulation. The main concept behind differential PCM or delta modulation is, instead of transmitting the quantized values, let's first transmit, okay, the first level we will transmit, then next level we will not transmit, rather than we'll transmit difference of 2 levels. Because you see, this is the basic concept, that if you have a signal and if you sample it at a very high rate, I mean suppose 4 times next sampling rate, then the samples will be very nearby. So the consecutive 2 levels will have some correlation. They will not be independent. So from, suppose if you are given one level, let's say this as a one quantization level, you can easily predict what can be the next level. Then given the 2 levels, you can easily predict what can be the next level. So these levels, quantization levels, or the amplitude of sampled signal, they are somehow correlated. It is this correlation which will be utilized in the concept of differential modulation. Now let's first develop some notation. Suppose m of k denote the kth sample of message signal which we have sampled, okay, and m of k minus 1, let it be the previous sample, k minus first sample of the message signal. Now what will you transmit is d of k given by mk minus 1. So from this example, what I can say, this is m of k, this is m of k minus 1, and d k is the difference. We can see difference is much smaller than the actual values, and transmitting difference will require less number of bits. Now if you recall what we have done while proving the quantization noise, that the quantization noise, if you represent by suppose q, and so the to calculate the error, we mean square error, so q square, and you integrate it dq, and how many levels are there? Since we are assuming the minimum amplitude minus mp, the maximum of mp, so the difference between the 2 levels is 2 mp, and we are dividing them into L different levels. So the width is delta V equal to 2 mp divided by L. And the error we computed by taking the midpoint analysis. So if this is delta V, so the error, to compute the error, we will integrate from minus delta V by 2 to delta V by 2, okay. and this is the quantization error. And what is the distribution of this? So it is uniform distribution, that is 1 over delta v, and this quantization error was proved to be delta v square by 12. And if you substitute delta v equal to 2 mp by l, then this quantization error will be equal to mp square by 3l square. Okay, now see what is MP in case of when we transmit the difference of the two signals. MP is the maximum value of the difference. You can see that this difference has very small value. So the MP here is reduced. MP is reduced, so MP square by 3L is also reduced. So hence quantization error is reduced with this scheme. So this is one of the benefit of differential PCM, which will be the same benefit which will be carried over in delta modulation also. We can do even better. Suppose instead of transmitting difference between current and previous sample, let's say that after transmitting several samples, we are trying to predict the value of mk, and let that value of message sample be m hat k. This is the predicted value. Then if our prediction is not correct fully, that is there is some error, then we define dk to be mk, which is the actual value, minus m hat k. How will be this done? Suppose with the help of previous values, suppose you have m0 to mk minus 1. With the help of these values, you see, we can predict, suppose this is like growing like this, we can predict the value of kth sample, and let that be m hat k. Then afterwards, when kth sample arrives, we can see difference between the actual value of message at kth point minus the predicted value. Then this d of k we transmit. Now to reconstruct, so to find the value of m of k, what we can do simply is, so receiver will add d of k with m hat k, because m hat k is a prediction which even the receiver knows, so it will get back the m of k. So this is the basis of differential PCM. In fact, what we discussed earlier, we can show that as a special case of this. So what is the simple prediction you can make about kth sample? Suppose you know the k previous sample k minus 1. So the best prediction is that m hat of k is just the, you put the value of previous. Okay, and that most of the times will be true. Suppose you take any signal like this, and if you take two consecutive values, if you sample them at much higher rate than the Nyquist sampling rate, then you will find that the next sample is nearly equal to the previous sample. Then in the next time you will get the actual value, and hence you will be transmitting difference equal to m of k minus m of k minus 1. And as you progressively do this, what you are actually doing is you are not transmitting the quantized value, rather you are transmitting the difference of the quantized value. That decreases the number of bit requirement, a lot. But does this have any mathematical basis also? Like, can you get some prediction from the previous samples? The answer is yes. We can use something called Taylor series. So if you take a function, this message as a function of time, and you compute the value of function at t plus ts, where ts is 1 over fs, sampling frequency, and is called sampling time. You know that fs is much larger, so fs, if you take the audio signal, you take usually 8 times Nyquist, the bandwidth. So it's like 8 times 4, it will be 24 kilohertz. In case of video, it is even much higher. So 1 by fs is 1 by 24 into 10 to the power 3, which is quite a small number. So what is the value of m of t around ts? So Taylor series says that it is m of t plus, then the second term becomes ts square by 2 factorial, and second term was this correct term is this ts times derivative of m of t plus ts square by 2 factorial, second derivative of m of t, plus so on. So there are other terms. So this m dash of t has a meaning. So I hope all of you know this Taylor series. We have done it, we do it in class 12th, and then it is repeated in BTech first and second semester. Anyways, So now TS is very small, so TS is the range of 10 to the power minus 4. So TS square is even smaller, so we can neglect the terms TS square, TS cube will be much less than TS. So we can approximately write that m of t plus TS is m of t plus TS times derivative of the m of t message. So this is very amazing signal, amazing equation. It actually tells you that if you know the current value of message signal, and you know the sampling interval, and you know the derivative of message, so you can predict the value of message at t plus TS. This is the future. So it shows that prediction is possible. It is not anything just an engineering insight. It has a mathematical basis also. Now we have some notation. So m, when you sample it out, so the kth sample is m of kts. It will be represented by m of k like this. So m of t, so kts plus minus ts. So this is actually equivalent to t plus ts, because at kth sample out of m of t is kts. So this can be then represented as m of k plus minus 1. And we can approximate the derivative. So you see, you know the definition of derivative. Suppose you have m dash of t, which is d of mt over dt. So what is its definition by the first principle definition? We all know this. So we can approximate it. We can basically write m of t minus m of t minus 1 just divided by this one interval. Okay, now if we, instead of m of t, we write what is m dash at kts, so it will be approximately m of kts minus m of kts minus ts and divide by ts. Okay, for small ts, this is approximately equal to derivative of message signal with respect to time. And how do we represent it? So we can represent it by m of k minus m of k minus 1 divided by ts. Now you see, we can rewrite the previous equation which we got here from Taylor series as m of t plus ts. We will write as m of kts plus ts. You see, I recall that when you sample, the ts sample can be taken as kts. You start with sample here as ts, then second 2ts, 3ts and kts. So what it look like? So this m of kts plus ts can be written as m of k plus 1 as a notation. It's approximately m of k plus ts m dash of k. So m dash of k is what we got here, the derivative. So putting it back, we can write m of k plus 1 is approximately m of k plus ts m of k minus m of k minus 1 divided by ts. It gets cancelled out and we got, this is the first order approximation of prediction. So if you know this previous sample k minus 1 and you know the current sample, you can get the value of future sample in this way. Recall that we got this approximation by neglecting the higher derivative terms. So if you include second derivative also, third derivative also, fourth derivative also, and you approximate them, you can write a general prediction term like this. So you can write some constant times m of k minus 1 plus some constant times m of k minus 2 plus some constant times m of k minus n. And this will be, so you are basically having a sample of message signal k at k minus 1 time, then k minus 2 and k minus n. This will be a crude prediction of the kth sample, which we represent by m hat of k. So this equation is called the system which will basically do this, we call that nth order predictor. It is basically a filter. Okay, how do we realize this filter? So if you have done serial system, you can basically see that if you have a simple function, you are basically applying a 1 unit delay here, 2 unit delay here, and n unit delay here, and these a1, a2, an act as a filter coefficients. So what you can basically realize the filter like this. You have the input here, then you apply the first delay unit, then similarly you have second delay unit, so on and so forth, and delay units. Then you have these filter coefficients, then you just sum it up, and the output you get will be the prediction of the value of the message signal at time k. This is also called transversal filter. When you have these continuous delay elements, it's used as a linear predictor. I think I will stop at this point so that the video doesn't become too large. So I will make now a last separate video where we will discuss the actual structure of differential PCM and hence finally the delta modulation.